Hello and welcome to another tutorial on data analysis fundamentals brought to you by Creations. Today we will be talking on multiple linear regression, which is an extension of simple linear regression. It is used when we want to predict the value of a variable, that is the dependent variable or outcome variable, based on the value of two or more variables, which are the independent variables, also called predictor variables or regressor variables. Multiple linear regression allows you to determine the overall fit of the model and the relative contribution of each of the predictors to the total variance explained. For example, you might want to know how much of the variation in time spent watching TV can be explained by season of the year, availability of cable line, cable subscription, and family income as a whole, and also the relative contribution of each independent variable in explaining the variance. Assumptions. 1. The dependent variable must be continuous, and it may or may not be normally distributed. Two or more independent variables which are either continuous or categorical. No significant outliers. We can test this in SPSS using the Cook's distance, which should be less than 1 if there are no significant outliers. There should be independence of observations. We can test this in SPSS using the Dublin-Watson statistic, and we should have value between 1.5 to 2.5 if indeed there are independence of observations. There should be a linear relationship between the dependent variable and each of the independent variables, as well as the dependent variable and the independent variables collectively. We can test this using the scatter plot in SPSS. There should be homoscedasticity, same scatter plot, and the data must not show multicollinearity. Multicollinearity occurs when two or more independent variables are highly correlated. You can test this using the Pearson's correlations. And lastly, the residuals of the regression line should be approximately normally distributed. So if you meet all or up to 90% of these assumptions, you can run your data using the multiple linear regression model. To demonstrate, we will be asking the question, how much of the variation in time spent watching TV in a day can be explained by season of the year, availability of cable line, and family monthly income? Let us see this in SPSS. So here we have our data set, time in hours, which is the dependent variable. It's continuous. We have the independent variables. We have a season. We are in sub-Saharan Africa, where we have just two seasons, the dry and the rainy season. So we have season, 1 for rainy season and 2 for dry season. Then we have availability of cable line, yes or no. Then we have family income, which is in dollars. So we will run the multiple linear regression, and then we check for the assumptions one after the other. So we'll come to analyze, come down to regression, linear, then we send the dependent variable, which is time in hours, to the dependent list, and then we send the independent variables to the independent list. Then we come over to statistics. We check R-squared change, descriptives, parts, and partial correlations. Then Dublin-Watson. Click on continue. Come to plots. We plot our residuals, Z residuals, against our Z predicted values. Then we check normal probability plot. Continue. Come over to save and check Cook's distance. Cook's. Continue. And then okay. So we have our outputs, but then we're going to check for the assumptions. So we've seen that the dependent variable was continuous. Whether or not it was normally distributed, it's not of a big concern here. We have two, I think we have three independent variables, two categorical and one continuous. Then the third is the no significant outliers. So Cook distance. So when we come here, we see that there is a column that has been added, Cook distance. You could sort from highest to lowest to check if you see any value 1 and above, but you could also go right down to check, and we see that there is no value that is above 1, and so we meet this assumption. The next is that there should be independence of observations, Durbin-Watson. So we go to our output and we check the Durbin-Watson distance. Is it right here, and it's 2.1, which is between 1.5 and 2.5. So we meet that assumption too. Then the next assumption, we're checking for linear relationship. So we check our scatter plot. All the values should lie between -3 and 3. So if we come back to our output, we go right down, we will see that for the scatter plots, our values lie between -2 and 2, which is in between -3 and 3. So we meet that assumption. And then the next assumption is for the homoscedasticity, which is still the scatter plot. We have seen it is whole. Then for the multicollinearity, we are checking for Pearson correlation and we want a value not greater than 0.7. So we come to our output and come right up to Pearson, and we check for the correlation between the variables for time and season, 0.002, time and cable, time and income, and we see that there is up to 0.7. So we made that assumption. So far so good. And then we check for the residuals. Come back to output and go right down to plot and see how far our points are away from the line here. That a bit far. Normally the points should be as close to this line as possible. So the points they deviate from the line, and so we do not meet that assumption. So about 90% of our assumptions have been met. So we can interpret our multiple linear regression. So we can always take the descriptive statistics, the mean, the standard deviation. And if we come over to the model summary, we will interpret R squared. And what does this 0.118 mean? It means that our model explains 11.8% of the variance in the dependent variable. Though, if you look at the p-value, we will see that it is statistically significant. But this 11.8% is small. We should normally have something above 30%. And so we continue, look at the Anova here, which is testing the null hypothesis that the slope of the line is 0. So when we have this significant result, it means the slope of the line is not 0. That is good. And then we said in multiple linear regression, you can check the overall contribution of all the independent variables. So you can check that using the standardized coefficients beta. And if you look at that, you see that income had the greatest contribution. And if you want to check the contribution of each independent variable, you will check partial correlation. If you look at it here, you find out that income still had the highest contribution. Then looking at which independent variable actually can be used to predict the dependent variable, you look at the significance column and we see that we have cable 0.012. So the availability of cable line can be used to predict the time spent in watching TV based on our data sets. So thank you for watching. Remember to hit the like button and subscribe to our channel. See you in the next tutorial.